this video, we will focus on absolute convergence, ratio, and root test. A test for absolute convergence, the ratio test. The ratio test, let an be the series with non-zero terms. An converges absolutely if limit n goes to infinity, an plus 1 over an, absolute value of an plus 1 over an is less than 1. An diverges if the limit n goes to infinity, absolute value of an plus 1 over an is greater than 1, or if this limit is equal to infinity. The ratio test is inconclusive if this limit is equal to 1. When to use a ratio test? So when to use the ratio test? When to use the ratio test? Ratio test should be used when you see exponential functions, when you see factorials, and when you see like n to the nth power. When not to use ratio test, when you have a polynomial over polynomial, when you have rational functions, instead use a limit comparison or direct comparison test. Rational functions, polynomial over polynomial. Okay, so determine the convergence or divergence of the following using the ratio test. So we're going to practice the ratio test, and again it tells us about absolute convergence. Okay, so an is 2 to the power n over n factorial. An plus 1 is 2 to the power n plus 1 over n plus 1 factorial. So using the ratio test, we say limit n goes to infinity, an plus 1 over an equals limit n goes to infinity. An plus 1 is 2n plus 1 over n plus 1 factorial divided by an. Dividing simply means multiplying with the reciprocal. Now all we're going to do is simplify a little. So a little bit simplification. 2 to the power n plus 1 can be written as 2 to the power n times 2. N plus 1 factorial can be written as n factorial times n plus 1. And then I have n factorial and 2 to the power n here. Let's cancel between numerator and denominator all the common factors. So I'm left with limit n goes to infinity, 2 over n plus 1. And when n goes to infinity, this limit goes to 0. This limit goes to 0 when n goes to infinity. Okay, so if n goes to, this turns out to be it's less than 1. If it's less than 1, we have absolute convergence. We have converges absolutely. Absolute converges. Okay, absolute convergence. Next problem, we have n squared 2 to the power n plus 1 over 3 to the power n. So again, my an is n squared 2 to the power n plus 1 over 3 to the power n. An plus 1 would be n plus 1 squared 2 to the power, if I replace n by n plus 1, this would become n plus 2, 3 to the power n plus 1. Let's go ahead and do the ratio. Limit n goes to infinity, absolute value of an plus 1 over an. Limit n goes to infinity, an plus 1 is n plus 1 squared 2 to the power n times 2 to the second power divided by 3 to the power n times 3. And when I divide with an, we are actually multiplying the reciprocal, 2 to the power n plus 1. A small change here, when I broke 2 to the power n, I'm going to break it as 2 to the power n plus 1 times 2, because I want to be able to cancel between the top and bottom, numerator and denominator. Let's go ahead and see the common terms that we can get rid of. 2 to the power n plus 1 is there, 3 to the power n is there. So I'm left with limit n goes to infinity. We have 2/3 n plus 1 squared over n squared. And we know when n goes to infinity, this limit, because we have the same degree on top and bottom, remember the limits from calculus 1, this limit goes to 1, which turns out to be 2/3. And 2/3 is less than 1, which is less than 1. So absolute convergence. We have absolute convergence. Absolutely convergence. This series converges absolutely. Okay, part C, let's take a look at part C now, the next example for ratio test. Again, my term an is n to the power n over n factorial. An plus 1 is n, oh no, it would be n plus 1 to the power n plus 1 over n plus 1 factorial. Okay, so use the ratio test. Limit n goes to infinity, an plus 1 over an, limit n goes to infinity, an plus 1 is n plus 1 to the power n plus 1 over n plus 1 factorial times n factorial over n to the power n. Now I want to cancel some of the things between top and bottom. So let's rearrange things a little. N plus 1 to the power n. So n plus 1 to the power n times n plus 1. And then I have n factorial here. And then on the bottom, n plus 1 factorial. If I break n plus 1 factorial, I can write it as n factorial times n plus 1. And then we have n to the power n. So the n plus 1 cancels between top and bottom. N factorial cancels between top and bottom. Let us see what are we left with. N plus 1 to the power n over n to the power n. Again, this limit when n goes to infinity, because the top and bottom have the same degree, it turns out to be this limit goes to 1. N plus 1 over n. Let's see what does this limit turns out to be. This limit n plus 1 over, okay, so this one is a known limit. Let's go ahead and change that, rewrite it. So looks like we have n plus 1 to the power n, n plus 1 to the power n. This one is a special limit actually, n to the power n. This is limit n goes to infinity, n plus 1 to the power n raised to the power n. Limit n goes to infinity, 1 plus 1 over n to the power n. This limit goes to e. We have seen that in Calc 1. You can also go ahead and do natural log on both sides and then evaluate this limit. This limit turns out to be e. And e is greater than 1. If e is greater than 1, that means we have, if it's greater than 1, that turns out to be divergence. If your limit turns out to be greater than 1, then the series diverges. Our series diverges. Okay. Ignore earlier I said the top and bottom are the same degree. They're not the same degree. They are the raised to the power n. They're not rational functions. They're exponential functions. So that's why you cannot use the rational function rule here. Okay, this limit is equal to e. All right, and e is greater than 1. We know e is approximately 2.7, so we can say this series diverges. Next example. Okay, in the next example, we have, okay, so an is negative 1 to the power n, square root of n over n plus 1. An plus 1 is negative 1 to the power n plus 1, square root of n plus 1 over n plus 2. So let's go ahead and do the limit. N goes to infinity, an plus 1 over n, absolute value of it. So we'd have limit n goes to infinity. We can split this negative 1 to the power n plus 1 into negative 1 to the power n times negative 1 square root of n plus 1 over n plus 2 times the reciprocal of negative 1 to the power n square root of n. Okay, now let's see what can we get rid of between top and bottom. These are gone. On the bottom I have n plus 2 square root of n plus 1. So let's because we have a negative 1, but since we're looking at the absolute value, that does not really make any difference. So I'm going to write it as square root of n plus 1 over n times n plus 1 over n plus 2. Now, if you remember your limits from calculus 1, where does this limit go when n goes to infinity? This limit goes to 1. We can divide top and bottom both with the square root of n and simplify. Again, here we can divide top and bottom with n and simplify. We can argue and say both of these limits go to 1. 1 times 1 is equal to 1. So with that, if my limit comes out to be equal to 1, then we just say the ratio test is inconclusive. It simply means the test doesn't tell me that if this series is convergent, divergent, I have to use something else. Ratio test is inconclusive. Ratio test is inconclusive. Okay, let's look at next. We have root test to determine the absolute convergence. Root test to determine the absolute convergence. Here's another test for convergence and divergence, the root test. You will discover that this works especially well for series involving nth powers. So whenever you see not their nth root, but instead when you see nth power, whenever you see something to the nth power, go ahead and use the root test, because we'll be doing the nth root, and the nth power and nth root will cancel each other. So if a and be a series, let a and be a series, if the an converges absolutely if limit n goes to infinity, nth root of absolute value of a n is less than 1. If this limit is greater than 1 or equal to infinity, the series diverges. If that limit is equal to 1, the root test is inconclusive. Okay. For some problems, you can use both ratio and root test, but one could be easier than the other. Or you could also use some other tests that we've talked about. There's 10 total tests to test the convergence and divergence of a series. Okay, so let's go ahead, and since we have raised to the power n, we are going to do limit n goes to infinity, nth root of a n. So limit n goes to infinity, nth root of a n, which is e to the power 2n over n to the power n. Limit n goes to infinity. Instead of writing nth root, I'm going to write as the exponent, which is the same thing. Now, e to the power 2n times 1 over n, this will turn out to be limit n goes to infinity, e to the second power. And the bottom will be n. When n goes to infinity, where does this limit go? It goes to 0, and that falls under the first case, which is less than 1. So that means this series converges absolutely. We have absolute convergence here. This series converges, absolutely converges. Absolute convergence. Okay, here's another example. Strategies for testing the series. Is there any more examples of the root test I have? No, that was it, but I would add a few more examples for the root test. But you get the hold of it. Let's see strategies for testing series. You have now studied many tests for determining the convergence or divergence of infinite series. The following guidelines can help you get started. First of all, you want to see, does the nth term approach 0? If not, the series diverges. Is the series one of the special types? Is it geometric? Is it p-series? Is it telescopic? Is it alternating? Can the integral test, the ratio test, or root test be applied? Can the series be compared favorably to one of the special types? Can you use the comparison test or the limit comparison test? So here's a bunch of examples where we're going to use different tests we've talked about on different series. So p-series test, geometric series about convergence, divergence, telescopic series. We've seen ratio test, root test. We've seen nth term divergence test so far. Alternating series test we will be looking at the next section. Okay, so let's check. Determine the convergence or divergence of the following series. Okay, so we have summation n equals 1 to infinity n plus 1 over 3n plus 1. Well, this one looks like a really nice rational function. Nth term divergence test. Nth term divergence test said limit n goes to infinity an In this case, turns out to be limit n goes to infinity a n. That turns out to be n plus 1 over 3n plus 1, which is 1/3. If this limit is something other than 0, then the series diverges. The series diverges. Next example, summation n equals 1 to infinity pi over 6 to the power n. So this one looks like it is a geometric series with the common ratio equal to pi over 6. Let's see what is pi over 6 using the calculator. Pi over 6 turns out to be less than 1. That means the series converges. Again, we are not looking for what does it converge to. We're just asking if the series converge or diverge. Okay. N e to the power negative n squared. This one looks like I can use a u substitution here. So the terms are positive, continuous. So if I express the function f of x as x e to the power negative x squared, terms are positive, continuous, and decreasing for the function. So we can apply the integral test. We can do 1 to infinity x e to the power negative x squared dx. By using the u substitution, I can let negative x squared be the u. That would be 2x dx is what I need to have. So I'm going to multiply with 1/2, negative 1/2 to have the derivative there. So there's my du. This turns out to be negative 1/2 e to the power x squared going from 1 to infinity. If I plug infinity in there, negative 1/2 e to the power infinity plus 1/2 e to the power 1. E to the power infinity, that term actually goes to, this term will go to 0. And this is what we would be left with. Oh no, this would be e to the power, yeah, n is equal to 1 to infinity. That would be 1 over 2e. So there's a 1. So this integral turns out to be 1 over 2e. So we will say this series converges. Again, we cannot say it converges to 1 over 2e, but we can say that it converges. Okay. Let's check out our next example. Next series, 1 over 3n plus 1. This one we can easily do comparison test here. We know, we already know that 1 over 3n summation n equals 1 to infinity 1 over 3n is a divergent p series because my p value is equal to 1 here. And 3n is less than 3n plus 1, but 1 over 3n would be greater than 1 over 3n plus 1. So okay, so the bigger series, I can see the bigger series diverges. If the bigger series diverges, can we say something about the smaller series? If the smaller one diverges, then we can say the bigger one diverges. If the bigger one converges, we can say the smaller one converges. But if the bigger one diverges, then the smaller one may converge or may diverge. So this does not help. So direct comparison does not help. Let's go ahead and try limit comparison test. Okay, direct comparison does not help here because I could say the bigger one diverges, and that doesn't do anything good for me in the comparison test. So limit n goes to infinity. Let's compare an over bn. If this limit turns out to be a finite number, then they both converge or they both diverge. 1 over 3n plus 1 divided by the reciprocal. So limit n goes to infinity 3n over 3n plus 1. And this limit turns out to be, 1, which is, if the limit turns out to be a finite positive number, it's not 0, not infinity, then they both do the same thing. They both either converge or they both diverge. So by limit comparison test, the series n is equal to 1 to infinity, 1 over 3n plus 1, 1 over 3n plus 1, diverge. because we compared it with a divergent P series. Okay, part E. Before we come to part E, we will talk about one more test. We will talk about one more test, which is the alternating series test for absolute convergence, or we can skip part E for now. We haven't talked about alternating series test. We will do it in the next section. Let's look at part F. We have n factorial over 10 to the power n. Anytime you have factorials, power n's, it is helpful to go with the ratio test. So ratio test. So this one I'm skipping for now. Ratio test says limit n goes to infinity, an plus 1 over an, and that should turn out to be limit n goes to infinity, an plus 1, that would be n plus 1 factorial over 10 to the power n plus 1 divided by, multiplied by the reciprocal of an, because we are dividing with the n factorial. Okay, so we have limit n goes to infinity, n plus 1 factorial is n factorial times n plus 1 times 10 to the power n, 10 to the power n times 10 times n factorial. Okay, so let's see what can we get rid of. The n factorial can be gone between top and bottom. So I'm left with limit n goes to infinity, n plus 1 over 10. So when n goes to infinity, n plus 1 over 10, this limit goes to infinity. So ratio test says if this limit turns out to be infinity or something greater than 1, then the series diverges. So that is a divergent series. Okay, the next problem, this one we have something raised to the power n. Anytime you have a power n, it's helpful to do the root test. So let's go ahead and try the root test for this problem, because you see something raised to the power n. The root test says go ahead and do limit n goes to infinity, nth root of an, and that would be limit n goes to infinity, nth root of n plus 1 over 2n plus 1 to the nth power raised to the power 1 over n, because nth root is also the same thing as power 1 over n. When I multiply n times 1 over n, that is gone. So all I'm left with is limit n goes to infinity, n plus 1 over 2n plus 1. And we can divide top and bottom with the n over here, and this is going to come out to be, the limit would be 1/2, which is less than 1. That means we have absolute convergence in this case. This series converges. Again, what does that mean? That means if you write thousands, 2,000, 5,000, a million terms of this series, the sum will be a fixed number. The sum will be fixed. Okay, next we have section 10.6. Alternating series and conditional convergence. Alternating series test. Most of the tests we have used so far have dealt with only positive terms, other than geometric series. Most of the tests we've seen have dealt with positive terms only. A series whose terms switch between positive and negative is called alternating series. An alternating series cannot have two terms of same sign back to back. Alternating series is expressed as negative 1 to the nth power an, or negative 1 to the n plus 1th power an. Okay. All right. This series will converge if two conditions are met. The first one, the little series an attached to it, if that limit goes to 0, as n goes to infinity, an goes to 0. That's the first condition. The second, the an should be a decreasing series. The an should be decreasing series. So think about if limit n goes to infinity, an is equal to 0, the effect of positive and negative 1 is not going to matter. So